So we introduced hash functions, and we finished yesterday looking at an example of a real hash algorithm, MD5. We'll not go through how the algorithm works. At the end, we'll mention MD5 and another hash algorithm, SHA, the secure hash algorithm, just some characteristics. But they're real ones that are used, and there are others as well. And we had a very simple example with this bit XOR hash algorithm to see how it worked. We're going to come back to some of the properties that are needed and look at them in some more depth of the properties of the one-way property and collision resistance. What about our simple example algorithm yesterday? We had an example where we had 12 bits of input message. And we generated a value C, which is really our hash value. We generated a 3-bit hash value in that example we finished with before the MD5 sum. We said at the start some of the properties that we need for a hash algorithm. We said we needed a one-way property. That is, it's easy to calculate given the message the hash value, but if I give you just the hash value, it should be hard for you to find the original message. So it should be a one-way function. What was the other property? The other property was that we don't have collisions. If I take the hash of one message, M1, and get a hash value, H1, and then take the hash of a different message, M2, and get a hash value, H2, the two hash values should be different. And we looked at how authentication was applied. It relied on them being different, because if an attacker could create a message which has the same hash value as another message, then they could fool the users into thinking that the message came from a particular user. So we require these properties of a one-way property and collision resistance. One-way property is difficult in that very simple example we went through, the bit XOR hash algorithm. That is, giving the hash value, work out the original message. It's got the answer from yesterday. What was the hash value from our calculation yesterday? Can you remind me? I think 001 is what we got. The one-way property is saying, given that value, find the original message. Okay, so that's one property that we require of a hash algorithm. And that was a very simple hash algorithm. Let's look at the collision resistance property. The hash algorithm we used yesterday, this bit XOR, do we get collisions? Yes, possible. Why? Okay. In the algorithm yesterday, we're going to get collisions, and in fact, in any practical hash algorithm, we're going to get collisions. If we went back to our original requirements of our hash algorithm, we take some variable size input message, M, and produce a fixed size output message. If the input message is larger than the output, then it means we need it, then more than one input will map to one hash value.
We call pigeonhole principle.
Pigeonhole principle. In our example here, the hash value is 3 bits. The total number of hash values is 8 in this very simple example. So in that example, there are 8 possible hash values. I took a 12-bit input. Let's say if I limited the message to 12 bits, the number of messages is 2 to the power of 12. 4,000 messages, if we limit it to 12-bit input, 4,000 messages can be in to the hash algorithm. Only 8 hash values come out. It's a many-to-one mapping. And one of our slides drew a diagram like this. We take many possible messages can come into our hash algorithm, and a fixed size or fixed number of hash values can come out. If the length of the message is larger than the hash value, then we will, in theory, get collisions. Because, as in this case, there are only 8 possible outputs. There are 4,096 possible inputs. That means some of the inputs must map to the same output. If we numbered M1, M2, all the different messages, there are 496 possible messages with a 12-bit length, and we map them to hash values. There are 8 possible hash values with a 3-bit hash. Then some of these messages will map to the same hash value. So there's no way to avoid that. If our message is longer than the hash value, which it needs to be in practice, we normally want a hash value which is small for practical purposes, and we want to operate on any size message, or at least messages larger than the hash, then we're going to have collisions in theory. But we've said that we don't want collisions. If we have collisions, then it's potential for the attacker to defeat the authentication system. We can go back and see, maybe. We go back to some of the examples. One of the examples with the digital signature, if an attacker can find some message which is different from the original message but has the same hash value as the original message, then they can defeat the system. Let's consider figure A in this digital signature. User A sent the message concatenated with the encryption using the private key of A, the hash of that message. That was our signature. That's this part. Attacker intercepts that. What can the attacker do if they can find some message which produces the same hash value as M?
You can change the message. They have the same hash value as HTML.
So we can change the message. So the attacker chooses a new message, M1, different from the original message. If they can find such a message, M1, which has the same hash value as M, then what they do is they just modify M to M1. Take the bits representing the signature and copy them in the output message. That is, if the M was 10,000 bits and the signature was 100 bits, for example, they would modify the first 10,000 bits to their new M1 and copy that last 100 bits, the signature, and attach it to M1 and send that. That is, they don't have to do the encryption again. They don't need to know the private key. They just take the ciphertext, the signature that was received, and attach it to M1. Send that to B. And B does the check when it receives. So what B does is they take the received message, M1, calculate the hash of that, and they take the received signature, decrypt using the public key of A, the received signature, and when you decrypt that received signature, you get HM as the output. The signature was HM encrypted with the private key of A. When we decrypt it with the public key of A, we get HM as the output. And to check, that is this comparison step, we compare H of M1 to H of M. And we said that if the attacker could choose M1 such that the hash value of M1 is the same as the hash value of M, then they'll be successful, because what B does now, if M1 equals HM, B believes this message. It believes it came for A, believes it hasn't been modified, which is wrong because the attacker has modified the message. So for the security of our signature here, we need to make it difficult for the attacker to find such message M1. Find some message M1 which has the same hash value as the original message M. That needs to be practically impossible for the authentication to work. That is, a collision should be hard to find. But we've just said that collisions happen because with a small hash value and a large size message, we need to map multiple messages to one hash value. That there is always multiple messages that when we hash them, we get the same hash value. We do have collisions in theory, so in practice it needs to be hard to find those collisions. And that's how we measure the security of hash algorithms. How hard is it to find collisions? Any questions on that? Before we come back to the properties and look at them in a bit more depth.
Find some M1 that have the same hash value as the original.
Yes.
And used to decrypt.
That the attacker finds some M1 that has the same hash value as the original.
So the B has the same hash, so trust that.
Yes, so H of M1 equals H of M, therefore B trusts this received message when they shouldn't because it's been modified. So let's look at the requirements for our hash algorithm again, but let's look at them in some more depth and using a slightly different notation or terminology. We can say that if we take the hash of some value x using a hash function and get some value h, that x, the original message, is the pre-image of h. It's just the terminology it's used, and we'll see that used when we talk about collisions. The original message is the pre-image of the hash value h. H, the hash function, is a many-to-one mapping. That's what we see here. Many pre-images, many values of m or x, map to the same value of the hash value, the same hash. So the hash function maps many input messages to the one output hash code, hash value. That is, H has multiple pre-images. H3 here, although I don't list them, has M2 as a pre-image, this M is a pre-image, and many M's, many different messages as pre-images. So there are collisions. If the two pre-images are not the same and the hash values are the same, then that's what we call a collision. If the hash of some message 2 equals H3 and the hash of some other message 100 equals H3 and H3 are the same, then that's a collision. Collisions are undesirable, as we just said here, because in the different schemes that we use hashes for authentication, if we can find a collision, then that potentially means that we can defeat the authentication system from the attacker's point of view. How many pre-images for a given hash value? If our hash function takes a B-bit input block, in our example, B equals 12, and produces an n-bit hash value. So in our example here, a simple example, our input block is 12 bits in length, our hash value is 3 bits in length. B is greater than n. There are 2 to the power of B possible messages. In our case, 2 to the power of 12 possible messages. There are 2 to the power of n possible hash codes, 8 possible hash codes in our example. On average, if our hash function distributes the hash values uniformly, then each hash value has 2 to the power of B over n pre-images. In our example, 2 to the power of 4 pre-images. That is, there are 4 messages that map to one hash value. What's wrong with that? Where's the mistake there? B minus n. 16 is not right. On the slide, it shouldn't be B divided by n. It's B 2 to the power of B divided by 2 to the power of n, which is 2 to the power of B minus n. This part. Sorry. It should read 2 to the power of B minus n, which in our case would be 2 to the power of 12 minus 3 is 2 to the power of 9, 512. That's correct. Each hash, look at our simple example first. 8 hash values, 4,096 messages. If the hash function evenly distributes when you take a hash of a message, evenly distributes the hash values, then each hash value has 512 pre-images. That is, 512 values of 512 different messages mapped to the same hash value. Why 512? We see 8 times 512 equals 4,096. 4,096 inputs, 8 outputs, on average 512 inputs mapped to one output. Eight times 512 is 4,096.
So 512 map on 8.
So there are 512 M's that map to H3. There are another 512 M's that map to H2. And another 512 that map to H1, and so on average. That is, assuming that the hash function evenly distributes those hash values. It would evenly distribute them if it was a good hash, or if it was an ideal hash function. Quite simply, the number of inputs divided by the number of outputs gives us the number of pre-images for a hash value. The pre-image is just the name of the input value, the message in our case. Yes. 2 to the power of b minus n, which is, it's simply the number of inputs, 2 to the power of b, divided by the number of outputs to the power of n, which is 2 to the power of b minus n. So that's the number of, that indicates the number of collisions that are possible in a particular hash function. We want to avoid collisions, or in practice we want to make it hard for the attacker to find collisions. We cannot avoid them. So how do we make it hard for the attacker to find collisions? How do we reduce the chance for the attacker to make a longer hash value? If our hash value was 4 bits, there'll be 16 possible hash values. So of our 4,096 inputs mapped to 16 possible outputs, which means 256 M's inputs mapped to 1 hash value. We've halved the number of collisions in that case, on average, to 1 hash value. But we need to keep the hash value short for practical use. MD5, the example we went through yesterday, is 128 bits in length. SHA, another one, is longer, 160 bits, 224 bits. So we're talking about hundreds of bits for a typical hash value. And the size of the input to the MD5 algorithm that we used yesterday, how big? How many bits? MD5 is 128 bits output. The example yesterday, we used 730 megabytes input. So MD5, a hash function in practice, needs to be able to support very large files, arbitrary size. So still there's many theoretical collisions in that case. So now let's summarise or list the set of requirements that we have. And we've mentioned a lot of these already. But the requirement that we need for a cryptographic hash function, variable input size. The hash function must work for different size inputs, different lengths of M. Yesterday I applied MD5 on a 735 megabyte file. I can apply it on a 10 megabyte file or 1 kilobyte file, and the hash function will work. And it will produce a fixed length output. MD5 will always produce 128 bits as output. Fixed length are normally small for practical purposes. And the hash function needs to be easy to compute. We saw yesterday it took several seconds for my computer to compute the hash of that large file. So relatively easy to compute, so that we don't have to wait for hours, days, months to calculate the hash. So that's from the perspective of the implementation and making it easy to use. From the security perspective, we have a number of properties. First is the one-way property. We've already mentioned that. Easy to go in one direction, but if you have the hash value h, it should be computationally infeasible to find the pre-image of h, y, such that that y, if we take the hash of y, we get h. That is going the reverse direction. That's called the one-way property, or also called pre-image resistance. Finding the pre-image of the hash value is hard. The algorithm should resist such a task. Another property is if we have some value x, some message, it should be hard, computationally, there's a spelling mistake, infeasible, to find some other message with the same hash value as x. I give you a message m, you know the hash value of m. It should be hard for you to find some other message, say m1, with the same hash value. We saw why that property is required, because if it didn't exist, our attacker would successfully break our digital signature authentication. This is another pre-image resistant property. Again, it should be hard given the hash value of x, or given some message and then the hash value of x, that message, to find another message with the same hash value, called the second pre-image resistant property, or weak collision resistance. Find a collision. That is, find two messages, or given one message, find another message with the same hash value that causes a collision. You're too fast. We haven't got to strong collision resistance yet. Okay? Then we'll try and answer your question. So there's two different names. You may see them in the literature. Weak collision resistance. The other one, strong collision resistance. It should be hard for an attacker to find any pair of messages with the same hash value. Also called simply collision resistant. Now, what's the difference between the two? Look carefully. The first one, weak collision resistance, I give you some message, x. Your challenge as the attacker is to find some other message with the same hash value. In the second one, strong collision resistance, you get to choose any two messages, x and y, and find any two messages with the same hash value. Which one's easier for you, the attacker? Out of these two, weak collision resistance or second pre-image resistant and simply collision resistant or strong collision resistant, which of those are easier for the attacker? They're properties which are easier to break. That is, we say that the property is that it should be computationally infeasible. In the first one, I give you some message, M. Your challenge as the attacker, find another message with the same hash value as M or X. Again, which one is easier for you, the attacker? Any other attempts? Why? Which one's easier? Look it up on the internet, that's okay, that's what laptops are for. The hash functions are known. The hash function, like an encryption function, is public. Yeah. Anyone else? What are you going to do? the challenge for the first, for weak collision resistance, your challenge as the attacker is, I give you a message. Of the set of possible messages, go find another one with the same hash value. The strong collision resistance is go and find any two messages with the same hash value.
Say the weak one. This is weak. Should be easier to break.
Which one's easier for the attacker?
Weak one.
That's the confusing part. Yeah. The second one is easier from the attacker's point of view. It's easier to have the opportunity to find any two messages rather than find the hash value that's the same as some particular value. Now, I don't know how much easier it is to explain, but we've got a different... I will try. Without going too much through the maths, let's try and look at a different case. Here, I offer you a bet, okay? I have 1,000 baht. I don't have it with me. I will pay you 1,000 baht if someone in this room has the same birthday as me. Now, when I say the birthday, I mean the same date and month, not year. Okay? And assuming that we don't know about everyone else's birthday, okay? The conditions are that no one knows anyone else's birthday. Birthdays are evenly distributed amongst people. There's no twins, there's no leap years and so on, but of the 365 days, I'll pay you 1,000 baht if someone in this room has the same birth date, day and month as me. So here's the bet that I'm offering you. And if they don't, you pay me 1,000 baht. Who wants to take this bet? You either get 1,000 baht or lose 1,000 baht.
No way.
All right. I'll give you... So think what you would do, whether you would take the bet or not. We'll come back to what I would do if you offered me the bet in a moment. Bet 2. I will pay you 1,000 baht if two people in this room have the same birthday. And if they don't, you pay me 1,000 baht. Would you take this bet?
More chance, but still not worth it.
More chance, still not worth it. So which one... So who thinks bet 2 you've got more chance of winning compared to bet 1? Yeah, with bet 2, any two people have the same birthday. In bet 1, you must have the same birthday as me. So of the 30 people in here, one of you in bet 1, for you to win, or for the winner, then there must be someone with the same birthday. That one day out of 365 is where my birthday is. One person has to have the same. With bet 2, any two people must be born on the same day and month. More chance of that happening. You can actually calculate the chance of it happening. In the handouts or online somewhere, there's an extra handout that does the calculations, but I just have the answers here. In bet 1, so this case, the requirement is that someone else has the same birthday as me. The way to calculate it is that you look at what's the chance that no one has the same birthday as me. So with my birthday is on one day, the chance that this person doesn't have the same birthday as me is 364 out of 365, because my birthday is on one day, and since his birthday can be on one of 365 days, then the chance of being on the same day as mine is 364 out of 365. Same for the second person. We'll not go through that. And it turns out the chance that no one has the same birthday as me is 364 over 365 to the power of the number of people in the group. Let's say there's 35 people here, then n would be 35. The chance that someone has the same birthday as me, as x, is 1 minus the chance that no one does. And the value, if you put n equal to 35, the number of people, well, I hope there will be 35 in this lecture, but if there were 35 people here, the value is about 9%. So you should not take the bet, because there's a 9% chance that someone has the same birthday as me. There's a 91% chance that you lose the bet. That's if there's 35 people in the group. More people, that will change. That will go up. Bet 2, you can do similar analysis. It's a little bit more complex, but not hard. The probability that any 2 people have the same birthday. They don't have to be the same day as me. Any 2 people have the same birthday. With 35 in the room, the chance that any two of us have the same birthday is about 85%. You should have took the bet. You would have most likely won, assuming random distribution of birthdays.
We can try now.
It's a combination.
Yeah, it's a combination. Again,
Choose one.
look at the probability that any 2 people don't have the same birthday. It depends upon the number of people.
So it's true. My birthday is on the same day as her.
Okay, there you go. Anyone on 6th of April? 6th of April. Okay, there's a much lower chance of that. Of course, it assumes that it's the random distribution of birthdays. Okay, in this group, maybe it would be successful, but this is about the percentage of times that it would be successful. Much more chance of this being true, 85% chance with 35 people than the previous case. This plot and these numbers are on one of the handouts on the website, if it's not in your there. This plots those values where n is the number of people in the group, and this is the probability. The red one is bet 1, the chance that someone has the same birthday as me. The blue plot is the chance that 2 people in the group have the same birthday. And you see with 35, it's around 9-10%, and in case of bet 2, it's around 85%. Much higher chance of finding a collision of birthdays if you get to select from any 2 birthdays than saying, given 1 birthday, find a collision with that birthday, which is the red case. Although it's not the same plot and the exact same equations, the same concept applies for our collisions of hash functions. So we can state what we arrived at there. The probability of a collision between any 2 birthdays is much higher than the probability of collision with a specific birthday, with my birthday. Same concept applies with hash functions. The probability of a collision between any 2 messages is much higher than the probability of a collision with a specific message. Therefore, since the probability is higher, it's easier or more chance for the attacker to find it. So the chance for the attacker to find any 2 messages that cause a collision is much higher than the chance that the attacker has to find a message which has a collision with a specific message. Useful party trick, this one. You get with a group of friends and offer the bet and see who takes it. So, in summary from that, from the attacker's perspective, strong collision-resistant property is easier to break. That is, it's easier for the attacker to find a pair, any pair, that cause a collision. Easier than finding some message which causes a collision with some message Y which causes a collision with a specific message X. Strong collision resistance is easier for the attacker to break than weak collision resistance. They are the three main properties which we require for a strong cryptographic hash algorithm. The other thing that we'd like is that the output of the hash function produces a random output so that it equally distributes the hash values. Because the strong collision resistant property is easier for the attacker, then it's harder to provide as a service. That is, most algorithms provide the first two properties, one-way property or the weak collision resistance, but not all of them provide the strong collision resistance property. This shows some example applications of hash algorithms and what properties they require for them to be secure. The one we saw using a hash and a digital signature, it should have the one-way property, pre-image resistant, should have weak collision resistance, and in some cases, depending upon the types of attacks, it should have strong collision resistance. As we see here, the attacker, if our hash algorithm did not have the weak collision resistance property, the attacker would be successful. That is, if the attacker, given some message M1, can find another message with this, given some message M, if the attacker can find another message with the same hash value, they'd be successful. So, to stop such an attack, we need the hash function to be weak collision resistant, or the other name is second pre-image resistant. If the hash function is weak collision resistant, but it is not strong collision resistant, which is the third column, then that's okay in some cases. There's only certain types of attacks where it's not okay from the security perspective. A password file, which we won't go into, we've got an entire topic on that, but we'll come back to this one. The password file, where we store passwords, a hash value of the passwords, only needs the one-way property, pre-image resistance. The others, it doesn't matter, or it's not so important. So there are different hash functions. They may have, or hash algorithms. They may be strong, or they may satisfy different properties. Depending upon our application, we could choose the hash algorithm that satisfies the properties that we need. So the last thing, or the top comments say that a hash function which is called a weak hash function satisfies the first 5 requirements from the previous slide, but not strong collision resistance. A strong hash function satisfies all. It is also strong collision resistant, or collision resistant. Of these names, these are the names used in the textbook in the current edition, pre-image, second pre-image collision. In the past, one-way property, weak and strong. I prefer the older ones. They're not as, well, they're a little bit easier to say, to explain. So try and get your heads around the differences between strong and weak collision resistance. Not the mathematics for comparing them, but knowing what is involved from the attacker's point of view and which one's easier from the attacker's point of view. almost finished on this topic, and then we'll change on to something else. So how do we attack? Well, how can we apply a brute force attack on a hash algorithm? Try to defeat any of these properties. For the first two properties, the one-way property or this weak collision resistance property, basically what the attacker has to do is that find some message y that gives a specific hash value. And what do as a brute force attack? Try all possible messages until you get one that produces the hash value you're looking for. So in our simple example, if I'm the attacker and I have hash value h5, what I do is take the hash of all messages until it gives me h5 as an output. And then I've defeated the one-way property because given the hash value, I've found the messages that produce that and also the weak collision resistance property. I can find another message that causes a collision. So the simple approach there is to try all possible messages. In fact, you don't have to try them all because we know that there will be collisions. It turns out that the number of attempts is proportional to 2 to the power of m, where the hash code is m bits in length. So with MD5, it's a 128-bit hash code. If we compare to brute force attacks on ciphers, MD5, according to these properties, take 2 to the power of 128 operations to find, to defeat one of the properties using a brute force attack. Approximate. It's the effort's proportional to that.
We have to divide by 2 for average brute force, like.
Okay, then the average you could divide by 2. Yeah.
So this is the worst case scenario.
The important thing is that, remember what we said with their properties? Strong collision resistance is easier for the attacker than weak collision resistance. And from a brute force perspective, the attacker, in terms of one-way property and weak collision resistance, is about the same. Because what they need to do, they have a hash value, in this case, find a value of y. That's the goal of the attacker, to defeat the one-way property. In this case, they have a hash value, the hash of x, find some y that also produces a hash value, but is different than x. So it's about the same. But with with strong collision resistance, it's easier because they get to choose any 2 messages, x and y, to produce the same hash value. Find any 2 messages out of the set of all possible messages that find the same hash value, and it turns out it's more complex than the analysis you do with the birthday problem, but you can follow a similar approach. It's proportional to 2 to the power of m over 2. Much easier than the others, the preceding 2. For example, MD5 is a hash algorithm that produces a 128-bit hash code. The amount of effort to break the MD5 algorithm with respect to the one-way property or the pre-image property, and also for the weak collision resistance or the second pre-image resistance property, is equivalent or proportional to 2 to the power of 128. You have to apply so many operations. But to break that from the perspective of a strong collision resistance property, is proportional to 2 to the power of 64. Much easier from the attacker's perspective. So in hash algorithms, it's easier to provide the first two properties, pre-image and second pre-image resistance. It's harder to provide collision resistance, strong collision resistance. So not all algorithms will have this property. They may not need it in some cases. These are dependent upon brute force attacks. You can do other attacks that depend specifically on the algorithm. And they are generally considered very complex. For example, there are attacks known that apply attacks on MD5, which is 128-bit hash value, which is equivalent to about 2 to the power of 60 operations. So using some knowledge of the algorithm, they get it down to 2 to the power of 60. Brute force on the collision resistance or the strong collision resistance a brute force attack takes equivalent to 2 to the power of 64 steps using cryptanalysis, using some known algorithms. They can improve upon that to down to about 2 to the power of 60, but not by much. It's only 16 times faster.
16 times.
Yeah, it's only 16 times faster than brute force. So brute force,
By some algorithm.
yeah, by some algorithms. So the algorithms are quite complex, although possible, not much better than brute force. So normally the hash algorithms are measured by the length of the hash value. SHA, another algorithm, uses longer codes, hash codes. Instead of 128 bits, 160 and longer, and makes collision attacks practically impossible. And let's just finish by mentioning some characteristics of MD5 and SHA. MD5, the message digest algorithm, Ron Rivest. He was in RC4, RSA, and RC4. Same guy. 128-bit hash, commonly used, still commonly used, but no longer recommended because of possible collision attacks. Because the hash code is too short.
Still active, working.
Still used on, yeah?
Like these people.
Yeah, it's still alive and around. Yes, still alive and actively working. Yep. There's a function in HTML to encrypt the password. I don't know about in HTML, maybe in PHP. Yeah.
When we send, normally to protect from sniffing the package, we usually use HTTPS to turn on.
There's two issues or two questions there. One is about in PHP, when you create dynamic web pages, PHP has a function to, you said encrypt a password, but it's not really encrypting, it's applying a hash on a password. It's a hash function, and you could choose MD5. I'm not sure if PHP still uses MD5 in the past. I think it may just use SHA, which is the next one. So most programming languages will have a library that you can apply a hash on some value. PHP, C, Python, whatever. Java as well. I used MD5 on the command line. Yep. So yes, on passwords, instead of storing the password, say, in a database, you develop a website. People need to log into that website. What you do is when they register, they select a password. You store that password in the database. Now when they log in, they supply their password. If it matches in the database, they are successfully logged in. But instead of storing in the database, take a hash of the value, a hash of the password, and store the hash value in the database. Then when you try to log in, you supply your password or simply a hash of the password. If the hash of the password that you supply matches the hash of the password in the database, then that should mean that the two passwords are the same. Because if the two hash values are the same, we assume the two passwords are the same. I don't want to say any more because we've got an entire lecture on passwords and how they're stored and how we use hashes. So we'll see that in some more depth. And in Unix systems, that hash is stored in the shadow file. Yep. Yeah, there's different ways, but normally you hash the entire password. That means if you want to reset your password, normally the administrator cannot tell you what your password is because the administrator can only see the hash of your password. They cannot see your real password. That's why in many websites now you cannot ask, administrator, I've forgot my password, please tell me what it is. If they've set up the site securely, they won't know your password. They'll only know the hash of it. Therefore, they need to reset the password for you, give you a new one, basically. But we're too far ahead. We'll have more depth of passwords later. MD5, secure hash algorithm, improvement, basically. There are different versions. The basic one uses 160-bit. The message digest is the hash value, produces 160-bit output, but there are variations. You can produce up to 512-bit hash codes. The longer, the stronger, and some characteristics. So SHA is more common now. The older ones, the original ones, have some weaknesses. But the newer ones are considered strong and secure. So there are two common ones in use that you'll see around. We'll see again when we look at passwords shortly in one or two topics, how we store passwords, how we use hash functions in passwords. And you've seen already in different programming languages, you have libraries for using hash functions. Any questions on cryptographic hash functions? What's the next topic? Similar topic, message authentication codes is the next one. But before we do that, if there are no questions, we'll look and discuss a little bit about the midterm exam. Feedback. Do better. That's the feedback. Do better in the final exam. More time. Let's just quickly go through some of the questions. Probably you've all looked. And we'll look at the end of some ways to improve for the final exam. You should not forget it, because even though we may not ask specific questions about DES and all that, many of the concepts we still use in the topics we're covering. You still need to know it. Some of the questions we'll go through answers. Question 1, that was the fill in the blanks. Average was 14.5 out of 30. Many questions, some were hard, some were easy. list of words to choose from.
Some vocabulary for us to fill.
I've done that in the past, maybe. Sometimes I can, but sometimes it becomes so obvious. There's only one word that will go in, yeah?
Why the midterm exam this year is really, really hard, really hard?
Oh,
You have the test look like quiz. Seriously.
some questions were the same as last year and previous years. Note that this class average GPA is the highest of the past few years. I hoped you would go a little bit better. Let's have a look at that and see.
So we need more time to do that.
Let's not go through these, but one of them, what about this one? Techniques that hide messages in fake messages in order to avoid others knowing secret communications. Now, I try to be nice when I mark, that is, I don't look for spelling mistakes, but you need to be close. Even if you make spelling mistakes, you need to be close. So steganography, and I even spell it wrong sometimes, so that's okay. So some people will give you some answers. This was marked correct, for example. It's a spelling mistake, but it sounds the same.
You give partial score for
Full score for this, the green ones.
It's okay.
Steganography. This is some of the answers that people gave. They're all close to steganography. They were all marked correct. These were incorrect. Okay? If you say that, so it's not about spelling, it's if I imagine you said it to me, whether I would understand what you were talking about. So needed a G in there, most likely.
If you like some head, if you like some
geography. So that's okay. Not correct. Not correct. Red ones were marked incorrect. Okay. You knew something was in that area, but you had to be a bit closer. These are answers, yeah. That's okay. Question 2, RSA. Again, very similar to previous years. It's just a typical RSA question. It may be phrased differently, but you had to do the same steps as you've seen in previous year exams. Average 2.5. Basically, you needed to realize first which key was used to encrypt. Thammasat sent to Steve a confidential message, therefore it was encrypted with Steve's public key, therefore as the attacker you need to decrypt with Steve's private key. But you don't know his private key, in particular you don't know D. You know N, but not D, so you need to find D. The way to find D is to the same way that Steve would have found D. Take the prime numbers, or find the prime numbers that multiply to get n. So you had to factor n into 19 and 23. Once you factored n into 19 to 23, you calculate the totient of n, then you find a D such that when you multiply by E, you get 1 mod 396. So basically you need to do the steps that Steve would have done to generate his key, except the challenge you had was that you had an N, you had to factor it into P and Q. When I generated the key, I chose P and Q and calculated N. But since it's a small number, you can factor it. And you find D is 13, and then you do the decryption. C to the power of D mod N. And it's small enough to do on a piece of paper, or to expand, or just use a calculator. LCG, okay, most people went okay. Diffie-Hellman, not so good. So you need to remember, in this case, remember how Diffie-Hellman worked. Check, you look at your own exam and check and see where you went wrong.
How to throw away your how to throw away your brain.
The first part of Diffie-Hellman, of course, you needed to remember the algorithms. That was perhaps the hardest for most people. The first one was simply find the secret by taking the generator value and the received value, what is it, y of the other person, to the power of 10 mod 19. That was the easy one. The second part, you had this equation. That is, you knew 2, 3 and 19. You needed to find x Steve. And the way I solved that, because I don't know how to find the primitive roots and do a discrete log, brute force. Try x Steve equal to 1. Does it produce the right value? 2, 3, if you got up to 7, and it didn't take long, you find when it's 7, 3 to the power of 7 equals 2187, mod 19 equals 2. Therefore, x Steve must equal 7 in that case. So you needed to do a brute force on that, but not many steps. The modes of operation. So this was different looking question than any years, okay? So it was about, firstly, the performance aspects of the modes of operation, and then I can't remember the next part. Let's see. The first one, okay. Normal DES, we can encrypt at 100,000 per second. That is, we can encrypt a block using normal DES 100,000 times per second. 100,000 blocks per second with normal DES. First thing you need to know is that normal DES use 64-bit blocks. Okay? Some people forgot or didn't know that. So normal DES, single DES uses 64-bit blocks, and therefore triple DES uses also 64-bit blocks. The only difference with triple DES and normal DES is that it operates 3 times. So if normal DES encrypts at 100,000 times per second, triple DES will take 3 times as long, or 33,333 per second. Because triple DES, from a performance or implementation perspective, is DES, DES, DES. Just different keys, but same block size. So, you need to know that DES has 64-bit blocks, and as a follow-on, triple DES, 3DES has 64-bit blocks. We have an 8,000-byte file. If we divide it into blocks, 8,000 bytes is 64,000 bits. 64,000 bits divided by 64 bits is 1,000 blocks. So you have 1,000 blocks to encrypt. We can encrypt at 100,000 blocks per second using 1 core. So therefore it would take 0.01 milliseconds per block. It's just 1 divided by 100,000 is 0.01 milliseconds per block. We have 100 blocks to encrypt. How long does it take? The next part you need to know, so then you need to find out, okay, the time for an 8 kilobyte file, 10 milliseconds, 1,000 blocks at 0.01 milliseconds per block, 10 milliseconds for the entire file. Triple DES uses DES 3 times. So instead of 10 milliseconds, it needs to be 30 milliseconds because it's 3 times. Then you need to know, can we implement it in parallel? Because we have a 4-core computer. This is the speed that we can do on one core. Okay, a 4-core computer means you basically have 4 processors. On one processor, it would take 10 milliseconds. If we could implement it in parallel, we would go 4 times as fast. But we cannot implement it in parallel. Triple DES, we cannot. Because triple DES encrypt one block, then the next block, and then the next block. The second block, or the second encryption, depends upon the output of the first. And the third encryption depends upon the output of the second. They must be implemented in serial. So therefore, we cannot implement the triple DES in parallel. We cannot distribute it across different cores. The same applies for the mode of operation. Can we implement CBC in parallel? And again, it's no, because CBC encrypt one block, and then the next block's encryption depends upon the previous one. So the encryption of one block depends upon the previous block, and therefore it must be implemented in serial. So we cannot make use of the 4 cores in this case. We only use one core, 10 milliseconds for one file, using DES, therefore 3 times as much using triple DES. Answer is 30 milliseconds to encrypt the file. With counter mode, we cannot encrypt triple DES in parallel, but we can encrypt using the blocks in parallel in counter mode. In counter mode, I take some counter, 0, encrypt and do an XOR. The next block, I take the next counter value, 1, encrypt and do XOR with the plain text. Each block encryption doesn't depend on the previous one. So what I do on one core, one processor, I do encryption of block 1. At the same time, encryption of block 2 on the second core. On the third core, encryption of block 3, and so on. I can encrypt 4 blocks at the same time because I have 4 different processors. Hence, it's 4 times as fast as the previous answer. So the answer is 7.5 milliseconds. I don't have the other questions. What were the last questions in the modes of operation? You'll have to look at the answers of the other parts of the modes of operation. I can't remember them. Playfair, rows column, not so hard, at least the first part. Shannon, genius, some random combination of letters, AF. Some people got mixed up B and E, or many people had EB. I think because why? I don't know why, but many people got everything correct except they had EB. There were 2 letters and they read them in the wrong order. But multiple people got that wrong. They got some marks, but just one pair was wrong. Rows, columns, a little bit harder. But here's the ciphertext. You just need to, we have a key of 5 characters. We break it into, what have we got, 4 rows. Rearrange those rows according to the key. And RSA. Ravesh, Shamir and Edelman, the makers of, where our RSA name comes from. So if you knew that, you could check if your answer was correct.
I don't know the word, so I check.
Yeah. You should. We've seen Ravesh's name 3 times now. RSA, RC4, and we just saw him in MD5. So you will remember him for the final term, final exam. They are common in this course. RSA is a main algorithm. But if you were confident in the approach, then or if you knew the approach, you'd got that anyway, even if you didn't understand. Straight from last year, have a look at the answers. They've been probably in the last 3 years, that question. Still people, and in fact we did that, although briefly, in the practice just before the midterm, the exact same question. Avalanche, random, some definitions not so good. Avalanche, change. If you take two different plain texts differing by 1 bit, if you encrypt two different plain texts which are very similar except by 1 bit differ, then the avalanche effect means that the two output ciphertexts should be different, significantly different. Same concept, encrypt some plain text with key 1, encrypt the same plain text with key 1 modified by 1 bit, the two output ciphertexts should differ a lot. How do you test a random number? Or test if a number is random? If you think of it as a sequence of bits, some random sequence, should have an equal number of zeros and ones in that sequence. Divide that sequence into subsequences. You have 1,000 bits. Count the number of zeros and ones. Should be 500 and 500, approximately. Divide that 1,000 bits into subsequences of 100 bits, and then look at each subsequence of 100 bits. There should be 50 and 50, and then 50, 50, and so on. Look at the lengths. If you have a sequence of zeros, of 4 zeros, 0, 0, 0, 0, in the entire sequence, count the number of such sequences, and similar, the number of sequences of 4 ones, and they should be the same. And there are other answers as well. Last one. Is it? Yeah. Again, what's the approach for this one? First, recognise that from the question that says there's no padding used. That means, so where does it say that? You discovered that no padding was used in the rail fence or was necessary. What does that mean? There are 28 characters in the ciphertext. That means the plain text must be 28 characters. If it was 26 characters of plain text and we ended up with 28 characters for ciphertext, we would have had to pad the plain text out to 28 characters. So that we know that the plain text is 28 characters long. Given that, we take the plain text, apply rail fence, and then visionaire. Therefore, if we consider the plain text and then rail fence, for rail fence we need to discover the depth. And you need to do a brute force. But you only need to do a brute force on 6 possible values. Because with a 28-bit plain text, then the number of rows we can have, if there's no padding, is either one of these 6 numbers. 1 row, okay, you could guess that I wasn't going to use 1 row in rail fence, because if you use 1 row, you get exactly the same output. So the options you have 2, and therefore you think you can guess it's not going to be 28, 2, 4, 7 or 14. That is the depth of the rail fence that you need to try. Let's try depth 2. So I don't know the answer. So I try, what if the rail, and okay, and you guess, because I make the exams easy, that I would make it a small number. Or I'd make it one of the 2, probably. 2 or 4. So I try depth 2. I have at the bottom the ciphertext as the output. At the top I have the plain text if I had a depth 2 on a depth 2 rail fence. Why do I get this? Depth 2 means, how do we write it? Because you've given the first word security, depth 2 means S, E, if it's a depth 2 rail fence, and because you know the first word of the plain text, then the start would be read like this. And because it's a depth 2, security, S-E-C-U-R-I-T-Y, followed by the other letters that we don't know. And here's 4, there'll be another 10 letters, because with a depth 2, 28 characters, 14 on the first row, 14 on the second row. Okay? And the way I've written that here is, okay, S-C-R-T, followed by some other letters that I don't know what they are yet. I wrote them as uppercase A because they're on the first row, E-U-I-Y, followed by 10 other letters. So we know 8 of those letters. We know the ciphertext that's given, and we know that the key is 4 characters long. So I've written the key as WXYZ, WXYZ, because we repeat the key. So now I look at the values of plain text and ciphertext that I know. I know S and K. S, encrypted with some key, gives me the output K. C, encrypted with some other key, gives me the output Z. Same with R, T, and I also know I, encrypted with the same key that was used here, is W, whatever the value W is. I, encrypted with W, gives me V. S, encrypted with W, gives me K. What is W? That's the next step. I don't have... So again, what I did was trying depth 2, write down the ciphertext. With a depth 2 rail fence, given the first word security, start writing it in the rail fence, put those words into the plain text and try our Visionaire cipher. So we know if I encrypt S with some key W, I get K, using a Caesar cipher. And if I encrypt I with that same value W, I get V. Is there a value of W that both of those equations hold? That is, you convert those letters to numbers, and with Caesar cipher, because that's all the Visionaire is, S plus something equals K, I plus that same something equals V. There's no such number. So that proves there is no such W that satisfies those two equations, proves that the depth 2 is wrong. It was not encrypted with a depth 2 rail fence. There should be some letter that if we shift S by that number of positions, we get K. I don't have the alphabet here, I can't remember what the value would be. If you convert them to the integers, you just get an equation. S plus, the value for S plus W, mod 26 must equal K, and I plus W mod 26 must equal V. You'll find that there's no W that matches both of them. Depth 2 is wrong. So we try the next depth. Depth 4. Same approach. S, E, C, U. We write the known plain text as a depth 4. The rest we don't know. And I read that SR followed by 5 letters. Why 5? There should be 7 per row. We have 28 characters, 4 rows. We have 7 letters per row. So it's going to be in the plain text to the Visionaire SR followed by 5 letters. EI followed by some 5 letters. CT, U, Y. So with Visionaire, we take this plain text, we get this ciphertext, we know it's WXYZ is the key, the 4-letter key. Now we do the same. If we encrypt S with key W, we get K. If we encrypt I with key W, we get A. Is there a W that satisfies both of those equations? Turns out there is. W equal to the letter S. And we keep a try that for the others. That is, we encrypt R with X and get Z. We encrypt U with X and get C. What is the value of X that both of those equations are satisfied? I, W will be I, and Z would be T. And then, although you could be very, very, very lucky, you guess that that's the right keyword, SIT. So you've found the depth is 4, you've found the keyword is SIT, and now you've found the answer. Because you just apply the visionaire on the ciphertext with the key repeated, and you get the plain text, SRAROOH, and then apply the depth 4. Write that in 4 rows, and then read off column by column. And if you got that, you would have been happy. Have a look at the answers if you still don't follow some of them.
I used to have fun with cryptography.
You've still got time to get more fun out of it. Why was the average 42 out of 100? Too hard? Who didn't have enough time? Who didn't have enough time?
Not enough. I need 5 hours.
Most people finished within time, I think, had enough time. But yeah, if you got stuck on 1 or 2 questions, then you could have run out, for sure. Why? Exam was hard? Yeah. It was different, and I would... It was probably harder than previous years, I thought. Only a little bit harder, not much.
But the exam is how do you compare to last year? I mean, last year decryption just got only one method, right? But this year you got famous and then.
Last year, it was the difficult problems like the last question was easier, yeah, I think, yeah.
And the first part you got option?
In the last 2 years, there weren't this fill in the blanks. That was new this, or not so many at least. That was something different, and it worked okay. Why? Maybe because of our long days and short semesters. Maybe some of you don't understand the concepts, but understand the algorithms. That is, they can encrypt, you can encrypt and so on, but you cannot extend that to answering about the concepts. So that's something to pick up on. That is, it's not just about remembering how to do the mode of operation. It's be able to look at 2 modes of operation and see what's the difference in terms of security and performance. Not to remember so much, but to understand those concepts, even if we haven't discussed them in the lecture, to pick that up.
Maybe we can do decrypt, encrypt, and in the middle of yeah, but after nothing. The exam schedule.
Sorry?
The exam schedule. One of them, because we have 4 subjects in 2 days.
I see. So it was all...
All hard subjects. All hard subjects.
I understand. It won't change, I think. It may be a bit better in final because we're spread out, but not much we can do. Maybe not enough study for some people. So what can we fix in the next few weeks? We cannot fix number 2. Or number 1 I can deal with. Number 3 and 4. Number 4 you have to deal with because you need to find time out of all your 8 or 9 courses. Maybe with some more quizzes and some different examples, we'll try some more online quizzes which are not marked, where you can try and understand some of the concepts. So we'll try and have a few more of those. But we only have 3 or 4 or 5 weeks left, so we have to do it quite quickly. Okay, enough for today. Go home and study about authentication, hash functions, and we'll see you next week.